So now that we've computed the similarity values for the movies, we're in a position to apply the neighborhood predictor. We've actually made two assumptions in the development of this predictor. The first is that we're only using one neighbor. And that simplifies the math pretty significantly. And the second is that we're taking neighbors across movies. But we could have just as easily done neighbors across users, and the mathematical development is the same. So the equation for the neighborhood predictor is as follows. We want to take the baseline rating, and we want to add something having to do with this correlation. So it turns out that from the correlation values, what we really need to know is the sign of the correlation. Basically, we want to take the baseline and we want to either add or subtract the nearest neighbor's error. So what does this plus or minus sign mean? Well, the plus or minus sign is actually determined by the sign of the similarity. So if the two movies are very similar, then we want to add the neighbor's error, because we know that on the neighbor it was either too high or too low by a certain amount, and therefore we expect it to be the same with this movie. At the same time, if they were very dissimilar, then we want to subtract it, because if the baseline predictor was too high or too low, we would expect the opposite trend for this movie since they're very dissimilar. For instance, let's take user C's rating of movie 5. So we have C5. The first thing we need to do is we need to find the nearest neighbor of movie 5. So if we go into the table over here, which is the similarity values, we see that for movie 5, the nearest neighbor is 2. And user C has also rated movie 2, so therefore we can use the error in the prediction. Now, since 5 and 2 are positively correlated, that means we are going to add the error that we obtained in user C movie 2. So the error in user C movie 2 was 0.67, which indicates to us that the baseline predictor was too low by 0.67, and therefore we're going to increase it a little bit for the rating of movie 5. So we take the baseline for movie 5, which is 2.60 over here, and we add the error that the baseline had for predicting user C's rating of movie 2, which is 0.67. And we get 3.27. As another example, let's try user B's rating of movie 4. So we'll look at B4. If we look at movie 4, we see that the nearest neighbor is movie 2, and they have a very strong negative correlation. In fact, a perfect negative correlation. So therefore, we're going to want to subtract the error. And if we look at movie 2, we see that for movie 2, we had an error of positive 0.17, which indicates that the baseline predictor was too low by 0.17, but still we want to subtract from it because we're assuming that it's actually going to be too high by a certain amount because the movies are oppositely correlated. So we're going to subtract 0.17, and what we're going to subtract from is the baseline prediction of user B's rating for movie 4, which is 3.50. And so when we subtract that out, we're going to get 3.33. And we can take one other example. We take user F's rating of movie 5. So when we take F's rating of movie 5, we see that the baseline prediction was 3.85. And then when we look at movie 5, 5's nearest neighbor is 2 again. And F's rating of movie 2, we had an error of negative 0.58, so we're going to add this negative error because the baseline predictor was too high here, so we're subtracting out negative 0.58. That's going to give us 3.27 as well. And another important point to make is that in the case that the user hasn't rated the neighborhood movie, then we actually don't change the neighborhood predictor at all. So we keep the predictor exactly the same in those cases. And so if we continue along these lines, we're going to get the results shown in this table here, where this basically gives the neighborhood predictor for the entire set, all the different values. And again, we can compute the RMSE to be the square root of the sum of the squared errors. Again, it's a mouthful. But we're going to again look at the test data, 4, 2, 5, 3, and 4. And so we take 4 minus 2.80 squared plus 2 minus 1.50 squared plus 5 minus 5 squared, again that's a perfect prediction, plus 3 minus 3.33 squared plus 4 minus 3.27 squared. And we take the square root of that and we divide it by 5, which is the number of elements. And we get the square root of 1.44 plus 0.25 plus 0 plus 0.11 plus 0.53 divided by 5, which is equal to 0.6826. And this is an improvement of 33% over the original simple average predictor. And on the test set, or on the training data set, we actually have an improvement of 68% if you carry out the similar computations on the training data. And so these improvements are actually higher. It's an extra 5 or 10% over what we saw in the simple baseline predictor. So we can see how leveraging the similarities between neighbors can also help us squeeze a little more improvement in the RMSE. One other point we should make, though, is that while we expect the overall RMSE to go down, and it won't necessarily always go down, but we expect that it will, it's not going to be the case for each individual part. Remember, the neighborhood predictor is a heuristic that we use, so it's not guaranteed to reduce the RMSE on any given value. And for instance, we had user F's rating of movie 5. We predicted a value of 3.27 with the neighborhood predictor, and before, with the baseline, it was 3.85. And the actual rating was 4. So the baseline predictor was actually closer for user F's rating of movie 5.